to put there, right? 521, 522, 523, and 524. So there's 4 different things that can go in the first 3. And I'm just thinking of that as one thing. They're not 3 different numbers. Because you had 4 choices that could go in this spot. And then you had 10 different digits that could go in here, 10 here, 10 here, 10 here, 10 here, 10 here. So you end up with 4 times 10 times 10 times 10 times 10 times 10, which basically comes out to be 4 million. It's just a straight multiplication.
Because I could
And
tell
I
you
can
because
put
there's
0
0
through
to
9
9.
here, I can put 0 through 9 here. See, I could put any one of the 4 numbers, and then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, all the way up down through there. So,
Okay. Yeah.
yeah. The same thing as what we were saying with the 5-digit PIN. Basically, I can put 26 different letters here, 26 different letters in the next slot. And 26, I forget what that is. I think I got it somewhere on here. Let me see. Did I do it? Did I do it? So basically, I take 26 raised to the 5th power. And I get what, 11,881,376.
And I will go in the blank.
That's how many different 5-letter combinations I can make. And if I take it and make it case sensitive, then is little a the same as big A? If a password is case sensitive, is little a the same as big A?
No.
No. So if I came back and said that this was case sensitive, what did I do? If I said it was case sensitive, instead of being 26 times 26 times 26, it would be that would make it a little bit different. Now, if I said that you could only use each letter once, that would change it to a combination. Because if I only allow you to use each letter once you use A, you're not allowed to use it again, right? So if I said 5-letter pins, case not sensitive, okay? Once you use one letter, you can't use it over again. You can have no repeated letters. That's when it would be a combination. So if it said a 5-letter pin,
Well, I thought
and
combination. I thought combination is the one that doesn't matter.
each letter can only be used once. Then it would be a permutation because order would matter, and it would be 26 things taken 5 at a time, which then becomes 26 factorial over 26 minus 5 factorial, which basically comes down to be 26 times 25 times 24 times 23 times 22.
2.
And I can actually do this as a basic counting problem. I really don't have to use a permutation. Because if I can only use each letter once, in the first slot I can use any one of 26 letters. In the second slot I can only use any one of 25, and 24. So I can actually set this up as a permutation or a basic counting problem.
So if it's used once, then that'll be a permutation.
Yeah. Permutations and combinations are when I'm just using things once. And permutations, what's the difference between permutations and combinations? Order matters. The trickiest one on that, I think, for permutations and combinations on this, would have been this question right here. Where is it? This was probably the hardest one. There are blank different four-person committees that can be formed from a class of 15 people. Now, I was kind of nice because I gave you half of this one. Okay? But let's say I didn't give you this middle part. Let's say I didn't give you this. How would you do this problem? What is it? Four-person committees?
You are on the committee.
Okay. Well, remember, what does that mean? I gotta take all the committees that can be formed by the ones I'm on. Does that make sense? Well, how do I calculate all the committees?
All the committees would be the NCK.
That would be,
Equals-
if it's a committee, does order matter?
Oh, yeah. Oh, no, because not for this
So
one.
that's a
Combination.
combination.
Greg, where's your coffee cup?
In my office, on my, right there on my bookshelf by the door. It's a combination. How many things do we have?
We have the count, which is,
We had 15, and how many people were on the committee?
4.
4. So that gives me a combination, so that's 15 factorial over 4 factorial times 15 minus 4 factorial. Thank you, Mary. And I think I did that. Whoops. So basically, that's right here. Let me see if I can put this up.
Okay, wait, go back, because it looked like it said 40. Oh, that's the top one. Okay.
Okay? So that's this part right here. Which basically says if I do this, it's 15, I typed it all the way out. 9 times out of 10, I'm not gonna type this thing all the way out. 15 minus 4 gives me 11. So see this part that's striped out? I know it's going to get striped out. So basically I'm gonna write 15 times 14 times 13 times 12. Over 4 times 3 times 2 times 1. And there's my 1,365 committees. And I think I screwed up on this. Okay?
Why? That's what,
Because I made a mistake on when I wrote the problem.
oh, that's the number I came up with.
Yeah, okay, so you get 1,365 committees, that's right, this arithmetic is right.
The other one.
The place that I made the mistake is, I said that you were on how many? That was a mistake. I believe.
Oh, yeah.
Now, if I was doing this and I didn't give you that, this is all the committees I could form. How many committees would I be on?
That's the part I was trying to figure out.
If I actually was to calculate this and calculate this correctly, I told you it was 364. That was a mistake because I evidently typed the wrong number in. Changed the problem or something. But how would I calculate how many committees I would be on?
You have a 150.
No.
You take away one person, maybe.
Huh?
Is that where you take away one person?
I'm going to take away one person that I can choose because I'm on the committee, right?
Right.
So that means there's only 14 people left, right? And how many of those am I going to take? There's a committee of how many? 4. I'm on 1. How many people do I need? 3 out of the 14. So actually what I would have to do is calculate this again for the, how many different ways I can combine the other 3 people, which would then give me 14 factorial over 3 factorial times 14 minus 3 factorial. Which basically means that if I did that, I'd get 14 times 13 times 12. Because everything from 11 on down would be wiped out by this. Right? And then the other part of my denominator would be 3 times 2 times 1. Now, check my arithmetic. So 14 times 13 times 12 equals 2184 divided by 6
Equals 364. You're right.
equals 364. That means this one's wrong. Because I divided by 12 instead of by 6. I can't multiply. Whoops. And then this was 364. Okay. Which means that this becomes 364. And then this would become probably 26.666. See, when I calculated, I knew that when I did this afternoon, working through it, I got one answer and I knew, it's like, uh-oh, I didn't get the same answer both times I worked it. But you saw where I made the mistake. I divided by 12 instead of by 6 because I multiplied 3 times 2 and got 12 instead of 6. So the aspect behind this, it gets kind of tricky. How did I get the 364? It's just, if I'm on the committee, then I have 3 other people I have to choose, but I only have 14 people to choose them from. So like I said, that was the trickiest one. To me, that was the trickiest one to do. But I was kind of nice. I gave you the second part of that.
Mm.
Is that sheet that you were referring to on Lolima?
Not yet.
Where is it gonna be?
I might try to throw it up at the end of the night. I just have to proofread it.
Okay, yeah, so we can study that, to see how we get that.
Yeah. Next question.
I think it was 13. Let me look.
13. Oops.
Well, actually, before you even get there, 12. I just kind of curious what you're asking for the score since the. Are you just
Well, you
saying?
have to calculate your z-scores to be able to tell the difference between the two. How do you calculate a z-score?
Oh wow!
X minus the mean.
Over the standard deviation.
Okay, so the z-score is the x minus the mean divided by the standard deviation of the, and I'm gonna start using a little bit more subscripts, because this one I'm going to do it, so if I was actually doing this, I'd get the z-score for the ACT, which would be the ACT score minus the mean of the ACT divided by the standard deviation of the ACT. Since it's S, it's going to be S bar, not X bar.
What is that Greek letter again?
This one?
Yeah.
Middle sigma.
Sigma.
And then I'm going to have to do the one with the SAT also. Now, if I'm doing these, and I just went to the take-home roster where I had the SAT scores, or the Z-score comparisons, basically I got the mean, and I just wrote the formula real quick there that said take it. So for the SAT and the Z-scores, right here is the standard score for the SAT, which is 1.07. The ACT is 1.29. So which one's better?
The ACT.
Why? So,
Oh, why? Because it's bigger. Final answer.
huh? Why is that one better? Why is the bigger one better?
I don't.
I know you said.
Because if I did the same question for the next one, it says the Molokai race, I did these, which one of these is better?
The first year.
The first year, why?
Because you're faster in that year than the other year.
Yeah.
Well, you're faster in 2010 than you're in 2011.
Okay, so,
But the mean.
but this one is small. This one number's bigger. Somebody,
Okay.
huh? See, this is where you have to define it. In a race, which is better? A fast time or a slow time?
A
Faster score.
A fast time, which would be smaller, right? The smaller the time, the faster. 10 seconds is faster than 12 seconds,
Okay.
right?
Wait, why does it say the slower time would be a better race then?
Also, because when you're
Or
racing,
I should have said lower.
Lower?
Slower time. I should have
And
said,
then lower.
yeah, I guess I kind of misused the word slower there.
Oh, okay.
Because the time of, it wouldn't necessarily be it would be a lower Z-score. Because a race that I do in 12 seconds is better than a race I do in 15 seconds, right? So, but in a race, I want a lower score, a lower number. So in a
Yeah.
race, the lower number would be the better score. But on a test, I want to get the bigger number.
Yeah.
So on the test, the bigger score would be
That's
a
what I
better
said.
score.
That's what I
But see, you gotta
said.
be a little bit,
Oh, yeah.
the bigger number is better because the higher score
is better.
is better. Okay, so you gotta be a little bit more, you can't just say because it's higher. A
You know
higher,
what I meant. No.
a higher score on a test is better, a smaller number on a timed task is better.
It depends on what it's asking you.
You gotta pay, it's depending on what I'm looking at.
Looking at.
So if I'm looking at time, slower is, the lower the time, the lower the time, the faster I am. The word slower is badly used in here. So I should have had a lower time. It should, I should say lower time, not slower time. See, this is why I don't like putting things up sometimes, it's like slower, I make bad typing errors, and I don't always catch them, and then it gets a. But- So when I'm looking at this and I ask which is better, you can't just automatically say bigger is better.
And the Z-score helps us determine which is better.
The z-score tells me how far I am away from the mean. So the z-score just tells me how far I'm away from the mean. So by using z-scores, I have an idea of where I'm at in general compared to the mean without going through and looking at some basic different things.
How far I am from the mean.
Yep.
I thought the standard deviation was that.
The what?
I thought the standard deviation was each interval away from the mean.
The standard deviation is the distance from the mean, yes. The z-score, when I talk about a z-score, it makes the mean equal to 0 and the standard deviation 1. So the z-score just normalizes it. Where here I'm looking at a mean of what? 1026 and a mean of 20.8. How can I compare those? See, I can't compare them if I'm just looking at them.
Yeah, because if I had looked at just the standard deviation, I thought that the SAT was better because it was
Yeah, but see if I actually,
closer.
here's a picture of this.
because it looks like there's 2 standard deviations away for the ACT.
Really ugly pictures. Okay, so this is the ACT, right? And this is the SAT. What I have to look at is, what was the mean for the ACT? 20.8. Okay, so the mean was 20.8, and the standard deviation was 4.8. Down here, the mean was 1026, and the standard deviation was 209. So if I looked at that, here's the 1026. One standard deviation out here would be what? 1235. And out here, one standard deviation above would be 25.6. So it's kind of hard to look at that and compare exactly where I'm at looking at the different things. So that's why we take and get a normalizer standard score by taking the mean, taking the score minus the mean divided by the standard deviation. And what that in essence does is it makes this 0 and my standard deviation's 1 all the way across. So now when I calculate it and I get my z-score of 1.07 and 1.29, I can actually tell how many standard deviations away from the score that I am. Or how many standard deviations. So my score here of 27 is about 1 1/3, 1.29, above the mean. Whereas here, my score is just a little over 1 standard deviation above the mean. So this test score is better. So we use the z-score so we can compare things that don't have the same mean and the same standard deviations.
I feel like we've talked about this before, but since it's so long ago, I
Yeah.
have to remember.
Yeah.
But it's coming back.
Oh, yeah.
And we will be revisiting that over and over and over again. Okay. Next question. The one that I wanted to ask, the ones that I thought that you have to sort of really look at, is this one is really kind of tricky. Most people make it, because if we do a pie chart, what should our numbers add up to? 100%. If I add up these numbers, what do they add up to? 128. And if I run that all the way across, all of those add up to a little bit more than 100. So you got to be careful when you're looking at data. Why does that do that? We did this on the homework several times at the beginning of the semester.
It's supposed to not count the last two or counting this back.
Yeah, the last two counting Hispanics they get double counted. So we sort of ignore these two. And when we do that, and we add those up and just the green ones, they add up to 100%. So you gotta be careful. I'm going to guess that some of you use too many too many categories when you made your pie charts. You guys got that? I didn't catch anyone on that one?
Some of us didn't get to it. 13, 14, 16, 17. I don't recall ever doing these.
Is okay, 14 we didn't get to, 16 we didn't get to.
Okay,
But
good.
13 we did talk about this one.
13 we did?
Yep,
In this way, in this format?
Really? I don't remember anything like greater or less than.
Oh, that's,
so we said that the mean
no, that's a
was
confusing,
60 and the standard deviation was 5. And if we went out here to 65, we went up 1 standard deviation, right? Well, we talked about the standard curve. and you gotta sort of go back and think a little bit about this, and you gotta play a little bit. What was the area here? When we talked about being within plus or minus 1 standard deviation on a normal or standard curve, what was the percentage of the numbers that were in here?
The area is 1, right?
Not of this area. The area of the whole curve is 1.
Is it the 50%?
Huh?
Is it 50/50?
Well,
What was your question? I totally lost your question.
we talked about what made a standard, a normal curve normal.
That is 50/50.
Well, no, the mean was always equal to the median, which means that there was 50% above and 50% below. But there were some things that we talked about being, we talked about some other things that made it normal.
Hey, Megan.
We said that if you took your mean plus or minus 1 standard deviation, how much should be under the curve? I know I defined this over a couple of times. And I said, what makes this normal curve or a standard curve? When we talked about our distributions.
I don't remember at all.
Needs to be between 0 and 1?
Huh?
That needs to be between 0 and 1?
What need, no, that probabilities are between 0 and 1. Huh? The whole area of the curve is equal to 1.
What are you asking?
This was just a basic definition that we did back in chapter 1.
Uniform.
Not a uniform distribution. We talked about a normal distribution. And we said that 68%
Oh,
was always
Gotcha.
between plus and minus 1 standard deviation, right? Remember when we talked about that?
Week of class?
Huh?
Was this the first week of class?
Oh, I missed that.
Could have been close to that.
Yeah.
definition of a normal curve is 68% of all data
Well-
will fall between plus or minus 1 standard deviation.
Correct.
Yes.
Ask me if I remember that on a test, I won't.
This is critical that you remember this. This is the definition. And plus or minus 2 standard deviations